Hey everyone, welcome back to more AP Statistics. Actually, this is a very special video because it's the very last video in our series on AP Statistics and StatsMedic. We've made it to the end, and how do we celebrate the end? Well, we get to a finish line. Lesson 12.2, Day 2, how close can you get to the finish line? So here's the goal, at least as the goal would have been in class. We would get a car, a toy car. You know those ones where you pull them back on the carpet and you let them go and then they just keep on going? Yeah, we would use those, and the goal would be to get the team car to the finish line without going over. And the catch is, no one's going to tell you the distance that you have to go until later. So you get a couple of test drives. You can pull back your car for 2 inches, 4 inches, 6 inches, and 8 inches. And then you can measure the distance of those travels. Now, based on those pullbacks, these test drives, you should be able to come up with some kind of a mathematical model for how far your car is going to go. So we're going to have to look at some data that I've pulled from another experiment. Well, here's that data. Of course, answers are going to vary because everyone's going to do their own experiment. But for this one that I did, when I pulled back the car for 2 inches, it went 7.5 the first time. Pulled it back for 2 inches, it went 6.1 inches. 2 inches again, and it went 4.9 inches. So that's a pretty disparate values right there. When I pulled them back 4 inches, the first time it went 23.5. Second time it went 32.9. Last time it went 21. So that's pretty consistent for the 4 inch. 6 inch, 81.9, 59.5, and then 61.8. Getting a little bit less consistent here. And then when we pulled it back 8 inches, we got 115.1 inches, 105.2 inches, and then 83.1 inches. I don't know what happened there, but it just didn't go that far. So the idea is this. Because we have our data now, we're going to use that data, and we're going to create 3 regression models. Now, I know what you might be thinking here, like 1 regression model is bad enough. Why do I need to do 3? Well, I think you're going to see why. We're going to create a scatter plot, and then we're going to calculate the LSRL, and then we're going to analyze linearity using any strategies. We're going to show our work. So let's start off with the linear plot. If I just straight up plot this data, what would I get? Here's the data that I've gotten. Now we can see that it looks kind of linear, and certainly our R squared here kind of helps us decide on that too. And except for I kind of see a little bit of a curve, especially if I follow the top dots or the top dots in the scatter plot. Also, here in the residual plot, there you can see a little bit of curve going on there. Okay, so this may or may not be the best model, the linear model. Let's have a look at the quadratic data. So for the quadratic data, we're going to take the x-coordinate and we're going to square them because the y-coordinates are also squared already. An alternative way of doing this would be to take a square root of the y-coordinates, but for some reason I think we're deciding on this one. So let's take a look at the quadratic plot. So in the quadratic plot, again, just to re-emphasize what's happening here, we're squaring the explanatory variable, and we're leaving the response variable alone. Now, I have the least square regression line shown here, and yeah, this looks pretty good. And if I look at the residuals, well, is that a curved pattern? Not really. I mean, we have residuals above and below the line all the way through. And you might argue that this residual over here seems really low, but we do have residuals that are positive residuals. So I would say that this is okay. Also, we've got an r squared of 0.932, which is a good r squared. Lastly, what about the exponential curve? What does that look like? In the exponential curve, remember, we're plotting the x coordinates, the explanatory variable, versus the log of the y coordinates. Now this plot gets me, well, something kind of interesting here. Sure, this kind of looks linear again to the naked eye, but over here in the residual plot, I think you can see the curved pattern. Okay. All the residuals in the middle are above the, are all positive residuals, and all the residuals on the left and the right are negative residuals. So this is a pretty clear looking curve to me. Regardless of the fact that we still have a pretty high value of r squared, that curve in the residuals definitely kind of kills this model. So based on these three, what do you think? Which one is the best model? And most people, I would think, they would choose a quadratic model. And that quadratic model really really helps to take away the curve on the leftover curve that we see in the linear scatter plot. So, which regression did we choose? Now, first and foremost, we have to make sure that our residual plot shows no curve in it. That is really the thing that we're looking for. Barring that, or after that, if we have a couple of models that are kind of similar, then we would make our choice based on correlation and maybe even standard deviation of the residuals, S. So that's our choice. Our quadratic model is predicted distance is 1.9031 plus 1.6102 multiplied by the square of the pullback. And when we write it like this, we can see pretty obviously this is a quadratic model because we are squaring our explanatory variable. So how far do we need to go? 200 inches. So how far would we need to pull back our car to make sure that it goes 200 inches without going over? I think that's part of the idea here. So let's do some algebra here. 200 inches equals 1.9031 plus 1.6102 multiplied by pullback squared. At this point, you could really use the solver in your calculator. No one's going to mind that. But for our purposes, I'm just going to go through the algebra. We'll subtract 1.9031 from both sides. Divide both sides by 1.6102. And then we get the pullback is the square root of 123.02627. Or the pullback equals 11.092 inches, probably around 11.1 inches. So that's how far we would have to pull it back, or our prediction would be if we pulled our car back 11 inches, then we would hopefully travel 200 inches. If we did our math correct, if we chose a correct model, if everything goes our way, that is our prediction. So that was kind of fun. The next step in class would be to actually do this experiment, grab our cars and whatnot, and do what we need to do. So let's get to our big ideas so we don't lay you up here too long. This is about choosing the best regression. Which model works the best? So the first thing is check your scatter plot for a linear model, for a linear pattern, that is. If your scatter plot already has a linear pattern, then you're looking good. If you transform your data and your transformed data doesn't yet have a linear pattern, choose a different model. Which model do you pick? Yeah, you're going to just kind of go with your instinct a little bit on this. I definitely check the power model, and the exponential model, because usually those lead to pretty good results. Number 2, check the residual plot for a leftover pattern. If the residual plot has a leftover pattern in it, like the curve that we saw, let's look for an example. We saw a curve here when we tried the exponential model, then it's not a good model. However, if we don't see a curve in it, like in our quadratic model, then that's a pretty good model. Now, let's suppose we had a couple of different models and they all had a linear pattern in their scatter plot, and they all had a no leftover pattern in their residual plot. Then what do you do? Well, in that case, you would choose based on R and S. Remember, R is a number which shows us the strength of the linear relationship, and S is the standard deviation of the residuals. Ideally, R should be close to 1 or -1, and S should be small. Okay? So let's check our understanding, and we're going to be done with statistics before you know it. Many adults plan ahead for their eventual passing by purchasing life insurance. Many types of life insurance policies are available. Some provide coverage throughout the individual's life, whole life, while others only last for a specific number of years, term life. The policyholder makes regular payments, premiums, that's like a whole new vocabulary here, folks, to the insurance company in return for the coverage. The table shows monthly premiums for a 10-year term life insurance worth $1 million. Okay. If you're 40, your monthly premium is $29, 50, it's $68, 60, it's $157, etc., etc. The output shows 3 possible models for predicting monthly premium from age. Option 1 is based on the original data. Option 2 and 3 involve transformations of the original data. Each of the output includes a scatter plot with the least squares regression line added and a residual plot. The equations are given below. Okay, so for each of these models, let's predict how much a 58-year-old would pay for such a policy. So for the linear model, that's pretty straightforward. The predicted premium would be -343 plus 8.63 multiplied by the age of 58, and you get $157.54. Now, for the next model, which looks like natural log of age versus natural log of premium, this is a power model. We would get that the natural log of the predicted premium is going to be -12.98 plus 4.416 multiplied by the natural log of 58. That simplifies to 4.951. And then to get the predicted premium, that's going to be e to the 4.951 power. Natural log is log base e, so to undo that, we need to exponentiate using e. E to the 4.951 is equal to 141.3. I actually used the entire unrounded version of 4.951, so your result may be a little bit different than that. But if you use the full number and not round it, you should get 141.3. Anyways, using model B, we predict a premium of 141.3. Now our third model would be the natural log of the premium is equal to -0.063 plus 0.0859 multiplied by the age. There's only one natural log in this one. In this last model, we get the natural log of the premium is going to be equal to -0.063 plus 0.0859 multiplied by 58, which equals 4.9822. And just like before, in order to get the premium, that's going to be e to the 4.951 9822, which gives us 145.79. Now, if you take a look at all three of these predictions, 157.54, 141.3, 145.79, they're all pretty close to each other. So how do we decide which one of these is going to be the best model? Well, take a look at the residual plots. For the original linear model, this residual plot has a curved pattern to it. And then for the second one that we did, which would be the natural log of premium versus natural log of age, this is the power model. The power model also has a curve to it. And then the last one, the exponential model, yeah, there's not really a curve here. We have positive and negative residuals all up and down the length of our data. So because of that, I would say that the best of these three, I would say that the exponential function best describes the relationship. Now I would say that again because the residual plot shows no leftover pattern. The other two models, they both show a curve in their residual plots, so those models are not necessarily as good, probably not as good. And that does it, everybody. We are finished with 12.2 day 2. And we're also finished with the entire course of AP Statistics. Congratulations to you for sticking with it this long. And we've gone through some really good stuff today. We've gone through some really good stuff all year long. Good luck on your AP test, because that's what we're going to start studying for now. And we'll see you for more. Well, maybe not. Good luck on your AP test in any case. Have a good one, everyone.